Hello everyone. In this video, we are going to continue the last discussion about 1D peak finding algorithm. Now, in the last video, I said, is there any other algorithm that finds 1D peak in much more faster way? In fact, there is an algorithm called binary search, and we are going to use binary search to find a 1D peak in much more efficient time. Now, what is 1D peak? Let's look at the lecture note I took. Sorry. It's this one. So, like I mentioned, this is array index at 1 to n. Okay. First, we are going to look for an element index at n over 2 position. Okay. That means we just have the n element and we look at the element in that position. Okay. And if this element is less than to n minus 2 over 1 element, we have to look for this subarray, okay, which is to say the array index at 1 to n over minus 1. And if this number is less than n over plus 1 index element, we are look for subarray from n over 2 plus 1 to the n. Else, we are done, right? Because n over 2 position element is larger than or equal to the element index at n over 2 minus 1 and the element n over 2 plus 1 element. And we continue this algorithm. Let's say we have not found a peak in the first case, and if the element at n over 2 minus 1 position is larger than the element at n over 2, we look for this subarray like I mentioned. Okay? And we divide this subarray over 2. So, and we continue the same way until we find a peak, okay, or there is just one element. Now let's take a look at example. So this is previous example, right? This is same array. So the number of array in this case is 7, okay? And we first divide this array into half. So in this case, we are looking for the element at position 3. So this is Python. So this is position 3, actually this one 3, because this is index at 0, not 1. 0, 1, 2, 3. So we return 3. And we compare 3 to the next value. So we compare 2 to the 3. And we find that 3 is larger than 2. So we compare to the value next to it, which is 5. 3 is less than 5, right? So, like I mentioned, we look for this subarray, okay? And just we don't care this part. And how many elements in this subarray? 3, okay? Since 3, we look for the element at index 1 in this subarray, not the whole array, okay? So in this case, we have array subarray 541, and what is subarray 1, which is 4, okay? And we compare 4 to the value left to the value, right? Left value, which is 5. 5 is larger than 4. So we also discard this part and just look for this subarray. And then what happens in this case, the element of this subarray is just 1, right? So we just found a peak, which is 5. This same value as the 1, which is surrounded by this simple function or algorithm. Now, what is complexity of binary search in this 1D peak? In this case, we divide n elements into half, okay? So this is here. This represents that we have the elements. We have n elements, okay? And t means it's recursion, okay? We just divide and divide over and over and again, okay? Until their base case, which is number of elements is 1, okay? And what is theta of 1? This is time for comparing, right? In each division, we have to compare the element left index and right index. And comparison time is just constant, which is 1. And if you work out this equation, we get logarithmic time, okay? Log n, okay? Logarithmic n. And computer science algorithm, we denote log base 2, okay? It's not natural logarithm or base 10 in mathematical definition. And if you want to know why this division results in log time, you can check this Khan Academy website, running time of binary search. And yeah, so this is actual complexity. So this is the complexity of the previous one, a very simple or naive function. And this is complexity of binary search, okay? And if we have an element whose number of elements is 1, the previous naive function takes 1 complexity. On the other hand, the binary search algorithm takes 0 time or just constant time, because there's no 0 time, okay? If the value is bigger and bigger, we can see the difference, right? If the number of elements is like this one, log n is much more smaller. By visual inspection, we can see this difference, right? This is n. There's actually n log n, but it is very similar. if you look at n, this is very steep. If you look at log n, something like this, it's flat. It's not actually flat, but it's not as steep as n. Okay? In the next video, I am code this binary search algorithm in 1D Peak in Python. Thank you.